if I were to count the carbons in the substituent, I see that I have a 2-carbon, alkyne sticking against the benzene. And then over here, I see that I have 1, 2, 3, 4, okay? And specifically, I have, this branched methyl group on 3. So, we definitely have to do some sort of acetylide addition, right? That's the first idea. So what I'm gonna do is I'm gonna use some sort of base, so NaNH2, so sodium amide, dissolved in ammonia. And I only need one equivalent because there's only one terminal proton, right? So I can call that step 1. And then that's going to, effectively remove that proton because that's a base, and we get the acetylide anion as, the product from that first step. But then right after that, I can just say that I can, extend the carbon chain by, adding the alkyl halide. So what do we think our alkyl halide is going to be? Well, if we already have 2 carbons, then I just need maybe the 3rd carbon, which is right here, and then attached to that 3rd carbon, there's 2 methyl groups, so maybe something like that. So do you guys see how this could be 3 and 4? And then on 3, there's that methyl group. And I'm going to call that step 2. Okay, so the result of that step is really just an extended alkyne. So we have now 1, 2, 3, 4. So that's really the product of that first, series of reagents. Okay, and then from there, it looks like we need to somehow go from an alkyne to a product where the alcohol, there's only one type of alcohol, okay? It's racemic at that position, but it looks like it's definitely at the more substituted benzylic position. So I know I'm not gonna do alkyne hydration because that would form a ketone, right? We're not gonna do alkyne hydration, but what we could do instead is we could reduce maybe to an alkene, any alkene, and then add acid catalyzed hydration conditions. So let's think, maybe if I did, maybe a reduction, a weak reduction to bring this, alkyne to an E-alkene, that would be a 1, 2, 3, 4. So 1, 2, 3, 4, one's between 1 and 2. So that we get that structure. And then this is pretty obvious. You're one step away at this point, and you can just do acid catalyzed hydration conditions. Okay, any questions on this synthesis? Anybody? Okay. Does anybody have any questions from the exam that they'd like to share? Yes, you could absolutely also do oxymercuration. Great point. Great point. Okay, so about the exam. The average was what I expected. Typically, again, this is my 8th semester doing this. And typically, exam 3 and exam 4 is in the 60s. And that's exactly what we got. We got, I think, 63 or 64. So don't be discouraged. Like, that's normal for an organic class with all of you students in it. However, if you guys woke up this morning and checked your emails, I think you guys are pretty pleasantly surprised to see that you can literally get a 60 in this class and still pass. Like, I think that's pretty doable, like a 60 and get a C. And you could also, I think, now get to an 86, and that's still in the A- range. 86 is a really nice A-. So, especially for organic. So yeah, your grading scales are different now, and they're probably going to change again. So that's good, and they'll only go down. We're here to help you, not make you freak out. Okay. Yeah, exactly. I mean, I don't know. If you guys liked exam 3, then you're going to be golden for exam 4, because exam 4 is pretty much the exact same thing as exam 3. Okay. So, oh, thanks. Little mistakes. That's always what it is. And honestly, guys, if you had a paper test, don't be so hard on yourself, because if you guys had paper exams, like, you get a lot more partial credit typically. So that's why the grading cutoffs are going to be a lot more lenient, in terms of what Dr. Peterson just did. It's because normally you guys would get higher grades in all these exams. So give yourself a little bit of credit, because you're taking it multiple choice format basically, and that's hard. And are the averages similar for exam 4? Yes, they are. Okay. And I went through the test, before you guys took it, and I was pretty comfortable with everything that we discussed in office hours, being able to help you with the questions on the test, except for there's that weird like ring collapse or something like that. I was like, oh my God, what is going on there? But other than that, it was just one applied, I think, hard question. Okay. Yeah, and that's it. Okay, so let's move on to some radical stuff. So real quick, I'm just gonna talk to you guys about my research. So I actually do research with radicals. That's my main area of focus. So this is really cool. You guys you're not gonna be obviously tested on this. You can tune out if you don't wanna hear this, but I like to share this stuff with you guys. I think it's pretty neat. If you guys wouldn't mind listening to me speak for like 5 minutes about it. Okay, so here we go. So can you guys see this pretty okay? The full screen, I don't know if it's good. Awesome. Cool. So this PowerPoint was made by a researcher in my lab named Michael Sims. Really great guy. He actually taught a couple of the organic 1 classes for a little bit. He actually just got his PhD. But anyway, I modified this PowerPoint to be short and concise just to kind of show you what my stuff is. And we do something called raft polymerization. So I make polymers and I do this technique it's called raft, R-A-F-T, okay? So, oops, sorry. So basically, what is raft? Raft falls under this category known as reversible deactivation radical polymerization, okay? And this is really interesting. So like, I'm sure you guys have already seen in your lecture notes that these radicals can keep propagating over and over again until you have some sort of termination event. And if you don't know what I'm saying, it will make sense, you know, when we get there. But essentially, radicals can just keep, you know, adding onto each other until, you know, the 2 radicals find each other in space, collide, and produce what we call a dead chain, right? So essentially, what's happening here is we're going to exploit the fact that radicals can keep propagating. And if I have a whole bunch of monomers that I can keep adding, like, you know, monomer A, then monomer B, then monomer A, then monomer B, I can basically make these long polymer chains, these huge molecules via this method, okay? So essentially, we're kind of following the right side of this PowerPoint. So this is where I deal with. So left is the classic example. The right side of the screen is like what we're dealing with. So if you look, you can see that we have, you know, this main polymer chain right here. And each blue dot is a monomer, okay? One of those monomers. And then this red thing is called a CTA. This is our chain transfer agent, okay? So let's think about that. This is a chain, and this red thing we were calling a chain transfer agent. And then this is another chain. And this star, that's the active radical. That's a dot, basically 1 electron, okay? That's the radical. So when you look at this arrow, when you follow this, like, you know, equilibrium arrow below, you see that the chain transfer agent that I circled, I lost my mouse. Where's my mouse? Oh, there we go. You can tell that the chain transfer agent, oh God, there we go, moved to the other chain, okay? So that makes sense. And then the radical switched to the other chain, okay? So the radical above, which was the star on the right, went to the radical below, which is the star on the left. And then the chain transfer agent, which was the box on the left, became the box on the right. Okay, so you can see we have this kind of like throw a chain on, then throw a chain off, throw a chain on, and throw a chain off. So let's just talk a little bit more about that. God, this, I can't find my pen. Here, clear all drawings. Mouse. Okay. So this is what a chain transfer agent is. So that's what CTA stands for, CTA. And it has this kind of general structure. So you see that R, S, then that double bonds it to the S and to the Z. And what do all these letters mean? Well, R is just a carbon chain. You guys know that, okay? S is a sulfur, you know, and then this is another sulfur, and then Z is another group, okay? So there's an R group, a Z group, and then the S's are just sulfur. So you guys kind of know what that structure looks like. It almost looks like a carbonyl, right? But it's actually a carbon-sulfur double bond, all right? And there's a reason we use those, and we'll talk about them below. So over, you can see in the colors right here, dithiobenzoate, thiocarbonate, things like that. These are all just different types of chain transfers that you can use, okay? And notice the R groups are just R, R, R. And then you can see that here we have a benzene, and this is where I'm gonna expect you guys to like actually understand this stuff. So all the things before I didn't expect you guys to know, but you guys will understand this, which is cool. So essentially, you see that we have this, and I'm drawing these lines through it, okay? And everything to the right of those diagonal lines is the Z group, okay? So that's this Z group, okay? And let's look down here. So the Z group stabilizes this intermediate radical, okay, formed in the chain. So watch this. So see right here, PN, that just stands for a polymer, okay, a polymer. And this polymer chain is coming in, okay, one of these electrons right here. Let me draw an arrow. Okay, so one of these radicals, okay, comes to find this radical, and then the other pi electron stays to form there. Do you guys, if you guys know this topic already, then this is making sense to you, hopefully. So you can see that this radical that's on the PN polymer coming in is going to form a bond to the sulfur that's over here. Oh, this tool is so tough to use. Okay, so it forms this PN sulfur bond right here. We formed a radical on the middle, okay? And then that's basically the intermediate structure we have. Do you see that? Okay. Does everybody see this in the group, in the chat box? Somebody say something, just so I know I'm not just speaking. Cool, awesome. So now what do you think the Z group has to do? That Z group has to stabilize this radical, okay? That Z group stabilizes this radical. So look down here, electron donating Z groups reduce the reactivity, yada, yada, yada. So do you guys see why this amine would be a good thing to have here as a Z group? Because when you form the radical, the lone pairs on the nitrogen can actually resonate in, okay, resonate in slightly and stabilize or add electrons into that sufficient, exactly, you got it, Lauren. Okay, electron donating group. So it's basically what my research, and I'm just trying to prove to you guys, is it's all the things that you guys have learned. It's just a little bit applied, okay? So that's it. It's just, like how to stabilize radicals. We're gonna talk today about, radical stability and reactivity. And this is just an extension of that. So why do you think in the CTAs up here, the red, the yellow, the green, the blue that you see all up here, look at all of these groups. A benzene ring, why is a benzene so good? Ooh, because it stabilizes a radical via resonance. Why is the sulfur or the oxygen good or the nitrogen good? They all are electron donating groups and they all stabilize that radical. Awesome. Okay. And then the next thing we have to talk about is this R group. Okay. This R group is going to come off. So notice, this is the same structure we had before. So the polymer comes in. Okay. So the same fishhook arrows we see. We form this intermediate, structure. And what gets kicked off is this R group or the other polymer chain. So look over here. We see we have PM. Oops. We see we have PM over here. So PM is basically, they're just calling that the R group. And that's what comes off. And when this comes off, it can just add more monomers and more monomers. So if you're not following any of this, watch this. This is an animation, okay? This is gonna make it all make sense. Okay, so don't look at the left, just look at the right. Okay, so we have some sort of initiator, okay? So we'll talk about that today again. So we have some sort of initiator and I'm gonna maybe throw light at it, okay? So look at that orange, this orange spheres over here, okay? So once I add light into it, it's not clicking, oops. There we go, okay. They separate, okay? So one more time. So adding light, so look at that, initiator, so that's equivalent to the bromine-bromine bond, okay? So you guys see that up here? This is bromine-bromine, okay? Bromine-bromine, and let's say this is heat. We're adding heat up top, okay? So you get two bromine radicals. That's what we just saw. So this is Br2, for the lack of better terms, Br2 right here. Light, splits, really cool. Okay, so now you have a radical, okay? So now that radical can add to the blue spheres. The blue spheres are just monomers, okay? And you don't need to know this reaction, but we're just adding, you can see it, let me go back. So you can see we just added a monomer. That's what M stands for, okay? So we're starting to grow our chain and now we have a polymer forming, okay? So the red sphere, remember, is that chain transfer. That's the weird, and it corresponds to the color over here. It's that weird S, carbonyl, S, we have a Z group, an R group. Remember, the R group is just the other polymer. Okay, so watch. Now I find the chain transfer agent. Okay, cool. So when it adds there, the Z group stabilizes it. And then at any given point, that R group comes off. Boom, the R group coming off. And then that R group can add more monomers. Boom. Maybe it adds to another chain transfer. And then maybe that fragments off. And then adds more monomer and comes back and comes off and adds more monomer and comes back and comes off and adds more monomer and comes back and comes off, adds more monomer, comes back, comes off. Do you see that? And it happens over and over and over again until you get this long carbon chain, okay? And look at all these chains you're forming. And that's how you form polymers, okay? So this is a really cool topic I wanted to share with you. This is literally what I devoted 2 years of my life to, is adding to this type of research. And it's a new area and we're kind of exploring it a little bit more, okay? That's it. That's it. Hope you guys like that stuff. Okay. Just wanted to share. Okay. Hopefully that will make some more sense today with some new stuff. And if you guys are interested in research, if anybody's trying to get a research position, talk to me. Send me an email and we can discuss possibilities for you. Research is a really cool thing, especially in the organic department. Okay. So let's move into some real stuff. That's why you guys are here. Okay, so first thing we want to talk about is, what is free radical halogenation, okay? And I'm going to skip nomenclature again. I think it's a waste of our time because it really is the exact same thing. Now we're just adding an extra, halogen onto the groups. So it's just a waste, honestly. So the first thing we're going to talk about is radical stability. Okay, and you guys are going to love this. So we're on page 91 in the student workbook if you guys are following along. Okay, so page 91. Okay, this is really one of the easiest chapters. There's 3 reactions, okay? 3 total reactions. So I think it's an easy chapter, but we're on page 91, and we're going to be on question 3A, okay? So we are going to rank the following radicals in order of increasing stability, and you guys, okay, and rank the radicals in order of increasing stability. So you guys have kind of seen something like this before, but in the terms of carbocations, right? Okay, so nothing is new here. Okay, so here we have all these dots, and what a dot means is it's just a singular electron. That's what a radical is. So a radical is basically just a singular electron, not a lone pair. So compared to a lone pair, which would be the pair of electrons, so that would be dot dot. This would just be singular dot. Okay, and we have free radicals in our body. Okay. And this is a bad thing, okay? Free radicals causes damage in your body. So we want to get rid of these, and we do that by using antioxidants, okay? So antioxidants, like orange juice, vitamin C, ascorbic acid, all of these different things will actually quench these, get rid of them in your body so it can't cause damage. So make sure you drink your vitamin C today, okay? So essentially going from left to right, rank these radicals based on the names that they have, okay? So this would be a tertiary allylic, right? You guys see that? Tertiary allylic? We're good? Tertiary allylic? This would be a primary, but don't be fooled. It's too far away from that pi bond to engage in any resonance. So this is just a primary, okay? This one is just a secondary, no resonance, and this is plain tertiary. I think that's pretty much it in terms of the naming. I think that's pretty obvious. But now you have to ask yourself the same questions you ask yourself with carbocation stability. So that's kind of the main takeaway here, is that carbocation stability, this just means parallels, parallel lines, parallels radical stability. Okay, so everything you know about carbocation stability is exactly what you're going to do here. That's why I said it's nice. It's the exact same thing, so nothing crazy. So this whole classification scheme is basically just a way that you can recognize hyperconjugation. So that this has the tertiaries have the most hyperconjugation. They have the most carbon substituents that can stabilize that singular electron center. We don't have 8 valence, we only have 7 valence. Let me write that, 7 valence here. Okay, so these adjacent alkyl groups can lean in and stabilize it. Likewise, the fact that we can have resonance and delocalize that singular lone pair across space is also a stabilizing feature. So if you ranked it like this, 4, 3, 2, 1, you're right. Okay, are we happy so far? Nothing crazy. All right, let's move on to a couple other examples. Okay, so we're going to move on to 3B. Okay, so we have pH. And stop me if you have questions. And today I actually have to stop exactly at 2:30, so we won't be going over if you're worried about that. Okay, so I know I kind of abbreviated that, but again, remember pH, we've seen that before. pH is phenyl with YL, and that's just equivalent to benzene. So pH equals phenyl, I'll remind you guys over here, which equals benzene. Okay, benzene ring, okay? So you can just imagine that basically this position is the benzylic position, okay, and that's important. Oops, oh, darn, I didn't mean to do that. Okay, be careful. Okay, so classify these. This would be just a plain tertiary. It's too far away to engage in any resonance with the benzene. Okay, this would be a plain primary, okay? This would be a plain secondary, okay? And this would be a secondary, but secondary benzylic, okay? That should be enough for resonating all these, for ranking these. The secondary benzylic, remember I said is the best, so that's 4, okay? Then the tertiary, then the secondary, and then the primary. Okay, again, I think this is awesome. 3 points for your next test, okay? Let's keep going. Okay, so let's do D. I think we'll leave C for you guys, so we're gonna do D. Okay, here. Okay, and again, we're gonna go back to that PowerPoint that I showed you guys because I want to bring about like real realizations that you guys get. So anyway, again, rank these again. So we're at secondary. Let me do this in blue. So this is a secondary. Okay, but what does that aldehyde mean? What does this aldehyde do? And everybody put in the group chat: electron donating or electron withdrawing? Withdrawn, right? Because there's no lone pairs. So yeah, again, electron withdrawing, great. So that basically means that it's an inductive group, right? So this is induction. So this is a secondary induction, okay? And induction is a bad thing. Remember, induction is bad for carbocations because it pulls electrons away. All right, so bad. Here, what's this? This is a primary, right? Just a plain primary, okay? Here, secondary, again, but with induction. But notice the positioning of that secondary radical is a little bit farther away than, you know, that aldehyde is, okay? So we talked about that refrigerator example over and over and over again. If you're across your room, across your kitchen, and you're holding a magnet, you're not gonna be attracted to it. But if you're like right in front of that, you know, refrigerator door with a magnet, you're gonna like feel that attraction, okay? So distance matters. Here, this is secondary and just plain secondary, okay? So it's too far away to engage in any sort of, you know, resonance with this group. So what does this ester group get classified as, okay? Electron withdrawing or electron donating? Withdrawn, good. Okay, so even though there are lone pairs on the substituent, which makes you think electron donating, it's too far away to resonate. So that means that for all intents and purposes, this is just an electronegative, you know, basically halogen pulling electrons away. Let's see, Lauren, why isn't the primary induction? Why isn't the primary induction? Why isn't the primary induction? Oh yeah, I just skipped it. I should have said something. This is also induction. I'm sorry. Thank you. I appreciate that, Lauren. And Caroline, is the O not double bonded to the electron donating group? Caroline, can you elaborate a little bit more on that?
Yeah, why is that like a primary induction versus, because hasn't an oxygen before been a donating group?
Yes, okay, exactly. Great point. So these two examples, so let's look at these. So these both have lone pairs. So before, you know, let me just draw this down here. Like let's say this is benzene, and I, you know, showed you that. We would classify this as an electron donating group because we have the lone pair. So that's electron donating, right? Then over here, sorry, I'm all over the place. Let's just say I made it in amide. That's electron withdrawing because there are no lone pairs, okay? So here in these situations, yes, you do see the lone pairs, okay? You do see the lone pairs, but they're too far away to do any sort of stabilizing resonance with these radicals. They're too far away. They have to be adjacent, and they're not. So for all intents and purposes, you can just classify this whole group as a halogen or just an electron withdrawing, you know, inductive group, essentially. Does that make more sense, Caroline? Please?
Yeah, if it was closer though, then it would help like as a
Exactly. Yeah, so if the radical was here, right here, I'm gonna put it right here. If the radical was there, it would be a stabilizing feature. Okay? Because it's adjacent. So the radical is adjacent. Oh, there you go, Abby. Yep. Cool. All right, so let's rank these. So we know that there's induction going on in all of these, right? So if I needed to, you know, see which one is the best, it looks like the one that's farthest away is probably going to be ideal. So primary is the farthest one away. Then we have a secondary, okay, but it looks like the secondary, okay, I'm between this secondary, because they're both kind of one carbon away from the inductive group, okay? Now you have to ask yourself a pretty kind of hard question, which we haven't really seen yet. Which inductive group is less out of both of these, okay? So let's call this A, let's call that B. Out of A and B, which one do you think, the aldehyde or the ester, is going to be a less of an inductive effect? Okay, B, yeah, good job guys, B. Okay, So the answer is B. And the reason that is just take this ester for an example. Okay, so the electrons here, okay, this whole group, like these electrons are tied up in resonance, okay? But there is really no resonance going on here, like we're already at this carbonyl structure. So what's happening here is like all of these electrons, all of these electrons here are being hoarded to this side and pulling, okay, pulling away. So the induction is really strong here. But here, that's not true. This whole electron cloud on the right side isn't just pulled to one side. Some of them are tied up in resonance. So it's not as great of a pulling as you would have with just all of your electrons in this inductive group isolated here in this one spot. So that basically says that the inductive effect for A is a lot stronger than the inductive effect for B. So I'm gonna make it this ranking, okay? I might have lost some people there. So if I did, I'm sorry, and just tell me something and I can try and clarify. Okay. Oh, Madison, thanks, sweet. Okay. Awesome, okay, so let's go just back to this real quick. Let me show you something. Okay, so back to this PowerPoint real quick. Let me just, I gotta get out of all of this. Sorry. Okay, so back to this structure. So now this whole bottom line, I'm gonna highlight it so you guys know what I'm talking about. This whole bottom line now should make sense, okay? So we were faced with this problem where we generate this like intermediate radical right in the middle. So that's basically what we're doing. We're ranking all of these structures, okay? So we have a radical. And we are gonna say that, look, all of these electron donating groups, we even say it right here, electron donating Z groups, reduce the reactivity of this, whatever this molecule is called, due to resonance delocalization. So now that makes a little bit more sense. So the groups that are electron donating are going to stabilize those radicals, while the groups that are electron withdrawing are going to destabilize those radicals. So notice all of these CTAs that we're using in my reaction, my lab, we don't actually have any Z groups that are electron withdrawing because the reactions wouldn't work, okay? If it's electron withdrawing there and we're destabilizing those radicals, it's not going to work. But if we have radicals there, it will work. If we have donating, it will work. And that's what we see with the benzene, the S, the O, the N, okay? Are y'all kind of getting it a little bit more? Cool, I hope so. Get me out of here. Okay, so we're back. So we don't pay attention to primary versus secondary. Not in this case. What matters here is the inductive effect the most. Okay, good question though. All right, so that's it for rankings. I think that's pretty obvious. So everything else is going to come back. So make sure you guys know that. So now we're going to go on to question 4. So there's another way that we can ask this question. Guys, my Mac is about to die, so let me just plug it in. Sorry. Everywhere. Also, if anybody has a Mac, update it to the new Mac OS. It's so good. It's really, really cool to look at. They like updated all the icons and stuff and made it look nice. You have widgets on there. It's cool. Anyway, so we're on page 92, and we're going to be on 4A. 4A, okay? So basically what this question says is it's ranking the following molecules in order of increasing bond strength. Okay, so bond strength. So we're going to connect 4 and 5 together, okay? So just bear with me. So we have these series of molecules, okay? And I'm going to kind of do this folded structure. When I was making these questions and like in the software I was using, you have to like keep adding like methyl groups on top of each other to get these thickened lines, and they took forever. But here they are nonetheless. All right, okay. So we want to rank these in order of, Keisha, what questions do you understand? Is it 4 and 5 specifically? Is that what you're referring to? Yeah, great. Okay, so not great that you don't understand it, but great in the sense that like that's a lot of people don't get that, and we're going to talk about that in a lot of detail right now. Okay, so right now we're just talking about strongest bond. So number 4 equals the strongest bond. Okay, so let's think about this just logically. Like this is just purely logic. There's no chemistry here. Okay, if I have a really strong bond, it's because if I were to break that bond, the resulting products are not stable. I'll say it again. If I have a really strong bond, it's because if I were to break it, those products are not stable, okay? So I think that's a really, really good take-home message here. So let's just imagine I broke all of these carbon-hydrogen bonds and had radicals left over, okay? So basically what I'm gonna do is I'm just gonna draw a radical in the position of where all of these bolded hydrogens are, okay? So I'm just gonna draw it below. Here, here, oops, here, and here. So this is what would be the products of breaking these bonds, okay? So now rank these, or classify these. So tertiary benzylic, secondary benzylic, okay? Secondary primary, okay? So we're here. So essentially, this is the exact same thing you've seen before, okay? So if I were to rank this in terms of, radical stability, you guys could do that. But now we're doing it in terms of bond strength, okay? So the strongest bond is actually the one that's gonna form the weakest product, okay? The strongest bond is the one that forms the weakest product. Does that make sense? Because the whole logic I said before, the stronger your bond, the reason why it's so strong is because if I were to break it with some sort of energy that I give to the system, the resulting products are very, very unstable. That's why we keep this bond strong so that it doesn't break. Does that make sense? Because these products are bad. So this would be the strongest bond, actually, 4, strongest bond. Then the next strongest bond would be the next weakest product, or this one, and then this one, and then that one, okay? It's just the exact same thing, basically, that we just did in terms of radical stability, and you can memorize, but I hate saying that word memorize. If they ask bond strength, it's the opposite of radical stability, okay? There, I said it. I hate saying those things to you guys. Okay, it's just, and if they're asking for ranking in terms of bond strength, you can just imagine ranking it the opposite order of radical or carbocation stability. This only gets better with practice, so let's just do one more example of this. So we have, for B, we have, this structure, okay? Okay, so and we're gonna go back to freshman chemistry for a lot of you guys, and we're gonna talk about some cool insights in a second. And okay, I ran out of space, so I'm gonna go here. And I think some of you got, okay, so I've been inundated with emails about like your professor for next term and stuff. And I told you guys, like, this is just my opinion and you can do with it what you want. And anybody that feels some way about my advice, like it's just advice. So just take it as it is. Portmas is a brilliant man. He is so intelligent. He really is. And he has so much knowledge to give you guys, outside knowledge about the class. And if you're looking for that, take him. And he's going to really prepare you for an MCAT or if you want to go into the field. So I think that's a very good pro for him. Con is a lot of kids don't really want that. And a lot of kids just want the skeletal information that is enough to pass. And if you're one of those people, I think that's not the best option for you. For Dr. Guo doesn't really teach orgo that much. He teaches higher level organic classes like organic spectroscopy and things like that. So he's a very intelligent guy. I don't really know much about him, but I know he has, kids have told me that he has a thick foreign accent. So sometimes it's hard to understand him, but again, that should not be a reason for not taking him. And then finally, Dr. Brunner. Dr. Brunner, I think this is the first time he's teaching Orgo 2. He has taught Orgo 1 in the past with Dr. Peterson and Habeneck. So in terms of, if you want kind of like the same, I guess, vibe that you've already been having, I think Brunner would be the best, but he, again, only has one section. So that's kind of just my spiel on that, okay? That's my advice. That's just my advice. Would I recommend pushing Orgo 2? No, I do not. Because you need Orgo 1 for Orgo 2. I'm telling you, it all builds. Like, it's one of those weird classes where, like, you actually need to know the old stuff. And I don't, like, people that wait a semester, like, you're going to forget all your reactions. You really will. So don't. Just go into it. Yeah. I didn't say nothing more. So I'm a chem major. So I don't know if anyone's a major in this group right now. I'm also a chem major, and I didn't choose Orgo 1 or Orgo 2 for majors. Why would you ever do that? Like, sorry, why would anybody ever take the harder class? Like, so stupid, in my opinion. Again, like, I just, could you take Orgo 1 regular or take Orgo 1 advanced? I'm not taking Orgo 1 advanced. And that's literally my logic for that, okay? I'm with you guys. Just get passing and graduating. That's kind of the vibe. Anyway, let's do these. So let's break the bonds and let's imagine those products, okay? So here, okay, here. And I know that this is kind of sloppy, but okay, let's classify. So this is secondary allylic, this is good. Okay, this is secondary by itself, too far away. This is secondary induction, and this is primary, too far away, okay? So bond strength, again, the strongest bond is the bond that once it was broken formed the least stable product, okay? So out of the primary or the, out of the primary or the secondary, which one was the weakest? Well, the primary was the weakest, okay? This is not the best question because I'm looking at the secondary as well. Does anybody have the key pulled up? I don't have the key pulled up. She meant the induction one? Yeah, I figured for that reason. Okay, let's admit, okay. The reason why I'm having an issue, and if anyone's asking why, is because the primary and the secondary with induction are pretty close in terms of stability. So that's why Dr. Pearson was like, omit. Okay, so let's just omit this one for this problem. Again, I wrote these, so I sometimes overlook a couple of things. Again, so just based on these three structures, let's rank them. So the primary is clearly the weakest, so this was the strongest bond, okay, 4. Okay, then the secondary by itself was the next weakest product, so that was the next strongest bond. And then this one would be the secondary, like that's the most stable product, so that would be the weakest bond. I'm just gonna say 2 because we don't have enough structures, okay? So that's how I would rank these, all right? So that's how to do it in terms of bond strength. So the things that you have to recognize is the strongest bonds are the bonds that when they're broken form the least stable radicals, okay? That's the main objective of today. The next thing is we're gonna move on to question 5. So this is just, again, another way of phrasing all of these things, okay? So question 5, we're talking about ranking them in terms of bond dissociation enthalpy. So it's called delta H, BDE, and that's also known as the bond dissociation enthalpy. Okay, so we're gonna go back to freshman chemistry for a second. I know you guys are like rolling your eyes or something. I see you through your screens. No, I don't. But again, we're gonna do this very superficially. So again, when we talked about thermodynamics and stuff like that, you did do this. And remember, if we want to talk about the delta H of a reaction, we said that it was the, the sum of like, I guess it was like the number of moles times the number of bonds broken, like times the type, like number broken and times the type. I don't even remember all this stuff, but and it was always like reactants minus, and then the same thing, and then the products. Remember that? So it was like, yeah, yucky. And we don't need to know it now. We're in Orgo 1, so it's great. We moved on past that. But this was a thing that you guys learned, and this delta H reaction is that, okay? It's a measure of that. And remember when you had like tables and it was like, oh, I'm breaking the carbon-sulfur bond or things like that, and the enthalpy of that was like negative 300 kilojoules or whatever. That's what that is, okay? That's the bond dissociation enthalpy. That's how they come up with these values. So what does this mean? Well, let's kind of go into a little bit of theory. So there are 2 ways that you can really break bonds, okay? I'm gonna go here, sorry, one sec. Responding to a message. There are 2 main ways that you can break bonds, okay? And that's kind of like, I guess the big new thing in this chapter is that there's heterolytic and homolytic cleavage, okay? So let's just talk about heterolytic cleavage. And this is important, like this is, I'm not like just spewing, this is actually important stuff now. Heterolytic cleavage, okay? So let's just take like, for instance, an acetylide example. So we have acetylide anion, okay? And we know we have a haloalkane. Maybe that's like something like this. We know how to do this reaction already. Okay, so what happens is these electrons, these 2 complete electrons that are right here, are going to hit that reactive center, force this bond to break, and remember the 2 electrons in here are retained on that bromine. So the resulting structure would have been, remember, something that looks like this, a 2-carbon elongation. So it was 1, 2, 1, 2, 3, 4, and we have now bromine. Okay, so this is heterolytic cleavage because what happened is that both electrons in the carbon bromine bond were retained by that one bromine. Heterolytic cleavage. Okay, so it's involving 2 electrons. The 2 electrons were retained on this bromine. Okay, so these 2 electrons are these 2 electrons that are here. That's heterolytic cleavage. The new thing that we're talking about with radicals is homolytic cleavage. okay? So this is a little bit different. So this would be like, let's say I just for some reason have the same, example. And what happens is both electrons don't go to the bromine. One electron goes to the bromine and one goes to the carbon. So we're specifically focusing on that bond. I'm going to put a star here. This bond. What's happening to the electrons in this bond? And in here, two of them, all two electrons, go onto the bromine. Here, I'm going to draw these arrows. What's happening is we get two products where each one of those products retained one of those electrons. Okay, so notice it's one electron and one. Okay, that's why it's homolytic cleavage. Okay, so this is radical chemistry. Okay, so when we do this, when we did all these values back in Gen Chem, what these chemists do in their free time, fun job, they like literally do these reactions of every single little molecule. They do homolytic cleavages of all these little molecules. The energy that's given off by that, I know, free time. The energy given off by that is that value. So I just wanted to prove to you guys that where this stuff comes from, okay? Homolytic cleavage, that's radical stuff. They basically go one at a time, check every single molecule. Maybe they take methane, maybe they take ammonia, and they perform these homolytic cleavage reactions, and then they get these enthalpy values, and that's what we can use in real time, okay? Moving on. So now we're going to rank these in terms of bond dissociation enthalpy. So that should kind of give you some insights. So here, energy, okay? So remember, let's go back a little bit to Gen Chem. Energy is good if it's negative. Remember, he said if delta H is less than 0, that's a good thing, okay? Good things. If enthalpy is less than 0, that's a good thing. That's favorable, okay? So what we can think about is if the greatest bond dissociation enthalpy means the greatest positive number. Does that make sense? So this is the lowest bond dissociation enthalpy. I'm just going to call it BDE. The lowest bond dissociation enthalpy, which is the negative number, the negative one, that is going to be the most favorable, okay? Does that make sense? Like, you're only going to do this reaction, okay, if you form pretty stable products. And that's going to be apparent by a very low bond dissociation enthalpy, like a negative number, like a negative 300 kilojoules maybe, okay? As an example, I'm just like spewing, okay? But let's say I did this reaction and I got a value of delta H is, 732 kilojoules. I just threw that number out there, 732 kilojoules, okay? That's a really, really big bond dissociation enthalpy, and that tells you you have to put energy, it's endothermic, you have to put energy into the system to break this because it's so unfavorable to break on its own. That's not a favorable thing, okay? So the higher the bond dissociation enthalpy, the more unfavorable the reaction is. The lower the bond dissociation enthalpy, the more favorable the reaction is. Okay, let's look at 5A. So we're on 5A, and let's kind of bring that together. Let's take this home. And we are on pace with the class. Don't worry. This week we actually learned very little material, I think, because you guys had your exam before. So I think you guys are good. Okay, and again, we have these highlighted protons to be analyzing. Okay, so again, same thing. Imagine the products that would happen after now you understand what homolytic cleavage is. And again, something I didn't really talk about before is we've always used these double-headed arrows because that's 2 electrons. But we take one of those, like, I guess, left, like, I don't know, whatever you call it, whatever. And they're basically just fishhook arrows. And that indicates only 1 electron is moving in that arrow. Okay, so just keep that in mind. So essentially, the results of these structures would be a radical there, a radical there, a radical there, a radical there, okay? Classify all these. Secondary, okay, allylic, with that pi bond, allylic, did I spell that wrong? Allylic. Okay, this is just a plain secondary, it's too far away. This is a tertiary allylic, that's nice, okay? And this is a plain secondary, but secondary with induction, okay? So let's think about the stability of all of these radicals, right? So again, the lowest, I start with the lowest for these questions. The lowest bond dissociation enthalpy is the one that formed the most stable products, okay? So that would be clearly this one, so number 1. That has to be the lowest bond dissociation enthalpy because if it was this reaction, let's just say it was like this reaction, the energy given off was so favorable. It was less than 0, it's negative, it's exothermic because these products are nice, okay? You form this nice tertiary allylic, not this example. So if you maybe, formed this product that we're seeing down here instead of, this, it's very exothermic. Lauren, lowest bond dissociation enthalpy. equals most stable, right? Lowest foundation entropy equals most stable. Let me think about that. Lowest foundation. Yes, correct. Okay, 1. Okay, so it would be for this one. Then the next one would be, okay, this is the next, oh, sorry, not that one. This would be the next lowest bond dissociation enthalpy because it's a secondary allylic, okay, because it's a pretty stable product. Then the next lowest bond dissociation, we're starting to get high now, is probably this one. And then the last one, the highest bond dissociation enthalpy, is going to be the one that forms the most unstable products, okay? So you can kind of correlate bond strength to the energy required to, so again, the stronger that bond it was, that strong bond requires a lot of bond dissociation enthalpy, or a lot of energy thrown in there. It forms an unstable radical. Like, these are all things that you guys should, be bringing together in your brain. Okay. And Lauren, yes, I said correct. You're right for your thing. All right. Good there. Are we good? Awesome. Okay, so that's kind of like where we wanted to be with all of this stuff. And I want to go on to question 6. I'm going to leave 5B for you guys to rank. But so let's go on to question 6. And I think this is important. I'm going to pull it up on my computer. Okay, so let me pull this up for a second. Let's see. And what are we doing with time? Okay, we have 10 minutes. We're doing good. We'll probably get to the first reaction. Again, there's only 3 reactions in the chapter, so you guys are doing good. Here we go. And what page are we on? We are on page 93. Okay. Why isn't it opening? Sorry, guys, technical difficulties. What the hell? All right, for some reason it's not opening. Maybe it's a glitch with the new update. I don't know. Oh, actually, I think that just came. Oh, yeah. Sorry, almost there. Come on. Here we go. Okay, share screen, share. Boom. Okay. So here we are. And essentially, this is a really important, question to summarize. Did you understand everything I just talked about? So look at all these protons, HA, HB, HC, HD. And, these energy plots aren't obviously to scale, but just qualitatively, E1 through E4, we can plot that. So the bond dissociated enthalpy for E4 is going to be really high. So that means that it forms a really unstable product, okay? So take a second, look at this, and look at the radicals that form from, doing homolytic cleavage of all of those bonds, okay, that are bolded. Okay, so can you guys still see my paper if I have my screen shared, I hope? Okay, cool. So just pin me. If you guys don't know how to do that, you can pin me this at least footage, and then you're good. Okay, so this is HA. I'm going to call it A. And then this would be the result of HB. So that would be OCH3. And that would be this one. And then here, this would be nitro. And that would be that. And this one would be OCH3. And that would be this one. Okay, so we're there. So essentially, now we want to think about the stability, A, B, C, D, of all of these. So for A, that's they're all secondary, it looks like. But for A and B, there's a pi bond. Okay, so that's good. So it's secondary allylic. So we immediately know that A and B are probably more stable. It's more stable because, clearly we have a resonance happening with these pi bonds, and less stable because none. Then the difference becomes between the two substituents. So we have a nitro group versus the methoxy group. So the nitro group is really, remember that one Lewis structure you need to know is this, that, and that. Okay, osmium tetroxide is another one that you should know. But essentially, there's no lone pairs. So this is an inductive group, induction. So this is not so good. So I'll put a sad face. I don't know if you can see that. Induction, sad face. Okay. Then here, this is a good thing. These have lone pairs, so it adds to the resonance that's already present. So that's good. Resonance. So now, out of the more stable column, so which is A and B, we have the resonance one with the methoxy group, which should probably be E1, and this should probably be E2. Okay, so let's think about that. Let me draw it on the board. So essentially, this should be B, okay, and this should be A, okay, and we kind of proved that. HA and HB are both, adjacent to a pi bond, which means that resonance is definitely going to help delocalize that radical. So that's why those two are definitely down there. And then how did I know which one went where? Well, the methoxy group added to the resonance, whereas the nitro group was just an inductive group. So that's how I did that. And same logic for C and D. So C and D we know are two unstable products compared to A and B. But again, the nitro group is even more unstable because of how much that inductive effect is happening. And then D is a little bit more stable, and this actually, that's not true. They're both electron withdrawn. I didn't mean to say that. Sorry, Lauren. I almost did, but I didn't. It's electron withdrawn because it's too far away. So essentially, they're both electron withdrawn, but which one is worse? Definitely the nitrogen, because look at that Lewis structure. You have a nitrogen, oxygen, oxygen, all electronegative atoms. Here, this one is just, so let me put angry face. This one is only one singular electronegative atom, the oxygen, okay? So then to plot that, you would say D, so bad, going up, E. Oh, no, C. E, I don't know. Bad, and then that's a C. Okay, so hopefully that kind of gives you an idea of how to put all this together. So now you can ask yourself, rank, or which one had the stronger bond? Well, okay, clearly the stronger bond corresponds to up here. This is the strongest bond. So strong, oh God, this is not gonna go well with the trackpad. SB, there you go, strong bond, okay? And then down here, that would be the weakest bond, okay? And that's a good thing. Weakest bond doesn't mean bad. Weakest bond is a good thing because when you break the product in HA, it's stable, okay? Weak bond, okay? So this corresponds to a high delta, high BDE, that thing. And then this is a low BDE thing, okay? So these are all things that you should kind of be able to rationalize, okay? I think that's pretty good. Let's talk, do we have time? Yes, we have time to introduce our first reaction, and we'll move on, okay? And then I think that will be done for today. So it'll be good. So there are two types of reactions that falls under this one type, and it's bromination versus chlorination. Okay, so let me stop sharing this. Bromination versus chlorination, okay? And essentially what we're going to see is we have this main reaction scheme. So I'm just going to draw, this, okay? And we are going to subject this to Br2 and H nu. So H nu, I don't know if you guys remember this, basically E equals H nu. This is Planck's law. I don't know if any of you guys know this. So this is going back to quantum mechanics. This is Planck's law that basically says that energy in the world is quantized. So this is the shorthand notation. Basically, you're just adding energy. Okay, you don't need to know any of that. So know that the fact that this is just energy being added, and it's Br2 with it. Okay, so the first thing that happens, again, remember, when we don't have numbers, we have to ask ourselves, what happens when these two things interact first? Okay, so let's just draw that. So Br2, which is essentially the same as saying Br line Br. And then I'm going to draw this reactant arrow, which is H nu. Okay, that just stands for light or energy or things like that. Okay, so what happens is that that energy is enough, frequency to break this bond homolytically. Okay, so homolytic cleavage looks like this. Remember, one electron, fishhook arrow, gets retained on the bromine, and the other electron gets retained on the other bromine. So you basically get 2 moles, or just 2 equivalents, whatever you want to say, 2 moles of bromine radicals, okay? And this step, this first step is known as initiation, okay? Initiation, okay? And then now you have your main reagent. So your main reagent is this bromine radical, okay? So now you're going to subject that main reagent to the, molecule we have over here. So we have this structure, okay? And we have, let's just say this proton, that's right here. And here's another bromine, okay? So what happens in this mechanism, again, is that homolytic cleavage is going to happen throughout this whole mechanism. Is this is weird. So this is called proton abstraction, okay? Proton abstraction, okay? So this bromine is going to grab this proton by doing this. It meets in space. It's kind of weird, okay? So the proton, one of the electrons in the proton is going to meet with one of the bromines in space, okay, the bromine radicals in space, and form this HBr bond. So this is forming hydrobromic acid and essentially this tertiary radical. So you form HBr as a product. Okay, so then what happens after that is now you can react more with this center. So this was the first step of propagation. Okay, so propagation. Okay. So we did initiation, the first line, okay? And now we're on propagation steps. And essentially, you can take this radical, okay? And this is the key thing, okay? You do have two equivalents of bromine, but for your mechanisms, please write diatomic bromine, okay? After your first propagation step, just write bromine diatomic again as your main reagent, okay? So, and I'll explain that again. So this can keep reacting with more bromine in solution, and you can keep getting more radicals. So you get this new bromine product, but now you still generated more bromine. So you can see how you're continuously creating radicals even when you form a product, okay? And that's what I was showing in my research is like with these chains, once you throw a chain onto that chain transfer and you kick something off, that can add more radicals and more radicals and more radicals, and then it comes back on and then kicks the other one off, and then that adds more radicals and radicals. So propagation is this really, really interesting like phenomena that we can exploit to make plastic water bottles that you drink or the tires on your cars. Like those are all polymers that we make through the method, one of the main, not the main method I use, but you know, one of the methods. Okay. Oh wow. Biden just won Georgia. Sorry. Okay, so we're there. So that's our main product of this reaction. And then we have one more step. So we have a termination step. So essentially, I always just do this. I'm not even going to show you the other ones. Just show both of those radicals coming together. This is the easiest one, and you'll get 100% accurate every time. And then those two bromines come together. You get diatomic bromine again, and then you're done. Okay? So your mechanism for these is quite extensive. So you can see where Dr. Peterson is probably going to be like, show me what's a plausible initiation mechanism for this reaction? What's a plausible propagation step out of all these things, you know? And this is known as proton abstraction. And guys, it is 2:30 and I actually have a meeting, so I actually have to go into another Zoom right now. But we're gonna leave it here. I will give you guys an announcement. I'm thinking about doing a weekend session, maybe on Sunday, like obviously not game day tomorrow, but maybe on Sunday in the afternoon, because I definitely did not get to where I wanted to today. So stay tuned for an announcement. I'll talk to you guys soon. Hope this helped and have a good game day. Stay safe. Bye.